Okay. Calc 3, lecture 12. We start chapter 3, Euclidean vector spaces, and the first section is vectors in 2 and 3D space. So a vector, we can say that it is a translation of space. Well, it can be any space. And translation has direction and magnitude. And hence, vector has direction and magnitude. Now, let's look at something else, which you are familiar from physics. If point A is translated to point A prime using this vector V, and then translated to A double prime using the other one W, then eventually it is translated from A to A double prime, and that is the addition of two translations, the addition of this translation and this translation. So from here to here, we can say that it is translated via V plus W. So this vector plus this vector, in fact, is this vector. So V plus W is defined this way. And you can see from this definition, or let's say idea behind vectors, why we use this triangle rule, or sometimes they say parallelogram rule, to add vectors. So a vector takes this A to A prime, another one from A to A prime to A double prime. Therefore, it goes from A to A double prime through this one plus this one. So this vector plus this vector is this vector. This translation plus this translation is this translation. And in fact, that is perhaps the most important thing about vectors, how you add vectors. There's another thing which is important, and that is how you multiply a vector by some, say, number. So this is how you add vectors, say, physically. Let's see what it means if we... So, for example, if a translation is V, then 3 times V means what? Means you are going, this is in fact V plus V plus V, right? So it is like 1V, then goes here, from here to here, another one, and from here to here, another one. So A goes to A prime, A double prime, and A 1, 2, 3. And that's 3V. So a scalar, which we call this thing scalar, because it doesn't have direction. Scalars for us are real numbers. They do not have to be real numbers in, say, abstract vector spaces, but for us they are real numbers, and the real number doesn't have any direction. You might say it has direction because it might be positive or negative. Well, let's say it's just two directions, either this way or this way. But anyway, this is, we call it scalar. And basically we do not say it has direction. But this V has direction, that is a vector. It has both magnitude and direction. So what this does, this multiplication of scalar by vector does, it just expands this, and it multiplies the magnitude by 3. It doesn't change the direction. So the direction is the same thing. If it's negative, it goes the other way. But if it's positive, it goes this way. The same sense that it was. So that is how you multiply an integer with a vector. Now, if I said any real number times this vector, we can get this the idea from here and say, okay, this 3 times V just multiplies by, it is multiplied by the magnitude of a vector. So if I have any real number times V, we can say that this is just multiplied by the magnitude of the vector. either magnifies it, it makes it longer or smaller, depending on k, or even direction goes this way. So we have both, say, in a sense, defined adding vectors and multiplying a scalar by a vector. So, and these are the two things we need to, in fact, define vector spaces. We just need to define addition of vectors, and also this one is called scalar multiplication. And you see by this idea that the vector is a translation of space, this makes sense. I mean, both of them can be defined, and they comply with what students usually know from physics. Okay, so now let's so this vector, say v, well, let's say it is in dimension 2, xy. Because we are looking at this as translation of space, then this vector, well, we usually call this thing the initial point, and this one terminal point, okay? So in physics, you, I don't know if in physics you use that initial point and terminal point. Since this is a translation of, say, in this case, R2, it is applied to every point of R2. So it takes, for example, this point A to A prime, it takes point B to B prime, say, and so on. So in order to represent or draw a picture or graph it in XY plane, we can put it anywhere. We can start this vector, we can put the initial point anywhere in this plane. That is, in fact, the reason when you draw a vector, you can just draw it anywhere. Except, well, in physics, when you are modeling, for example, a force using a vector, you do something else. I mean, if a force is applied to something, say, and it's moving, for example, then you say, okay, this force is applied to this point. We're modeling force with vector, and the point of application, which is the initial point, becomes important. But for us, because it is a translation of space, it can be applied anywhere, and we can just draw it anywhere. Okay, so it has a direction, it has a magnitude. Now, how do we say represent them algebraically? So in R2, the vector is basically the same. It's like the same as a point, say. So we say vector A, vector V, and we either write AB, or remember we also write it like this. And we call this thing, say, the X component, the Y component, or the X1 component, X2 component, depending on what we name these two axes. And what we know, I mean, this notation is also used for points. So this AB, in fact, is a point in plane. A, B is a point in plane. This should be straight line. Okay, this point, this is a point in plane AB, and what it's like point 0, this is 0, 0, right, is translated to this point A. Okay, so in fact, as I said, since we can put the initial point anywhere, so this, in fact, is my vector AB. What I'm trying to say is that we do not distinguish between this point and this vector. And, well, we can picture vectors in 2 dimensions and 3 dimensions. These are just pictures. But in like Rn, when n is bigger than 3, we cannot really visualize anything, but we can just draw an arrow and say, okay, this is a vector. But anyway, at least in 2D and 3D, we do not distinguish between points and vectors. And what vector that starts here and ends at this point. Okay, so this point and this vector are basically identified with each other. So they are, in a sense, we can say that they are the same. Okay, so if from now on I write AB like this, for a vector, don't confuse that with a point. In fact, that's the point. That's in fact the terminal point of this vector. So let's see what addition of vectors mean. So let me, this is in fact the picture, so let me need more space here. So I want to add 2 vectors, say vector V, and let's say V is V1, V2, and vector W, and that is W1 and W2. Okay, so V is a translation, takes this point to this point, say A. And how does it work? So this V takes point 0, 0 to what point? This point is what? This point is in fact V1, V2. Right? And this one translates to some other point. Say A double prime. Okay. Okay, let's see if it goes in this direction with certain magnitude. Where is this one? What are the coordinates of this point? You see, it extends the x coordinate, it adds W1 to x coordinate and W2 to y coordinate. So this A double prime has coordinates. It was here, now it is at V1 plus W1 and V2 plus W2. Okay? And that is in fact coordinates of this point. Exactly, so that is coordinates of this point. So this vector, which we call that V plus W, this one is W. This vector that physically we call that W is in fact this vector. From this picture we have V plus W equals V1 plus W1, comma, V2 plus W2. Okay, so this point, this point has coordinates, V1 plus W1, V2 plus W2. Therefore, since we said that this is in fact translate, it is the addition of these two translations. So V plus W is this, in fact, because this is the same as this endpoint or the terminal point. So this is this. This, in fact, gives us some idea on how to add vectors algebraically. So if we are given two vectors, v and w, that's how you add them. Add the x coordinates and add the y coordinates, or add the first coordinate and the second coordinate, whatever you call it, and that is the addition of two vectors. And okay, now what is scalar multiplication? Let me do a picture for that one and give you some idea what is happening. So if this point, this is point, say, AB, and what is 3 times AB? So this goes another, and then another. So what is the x-coordinate of this endpoint? It is A, so it is 3A. And this is B, so it is 3B. Right? Geometrically, A. So that's 3A, and also for B. So 3 times AB, we said that this is 3 times AB, in fact is 3A and 3B. So that's how you multiply scalars with multiplying scalar by a vector. So we take these two ideas and expand this to any dimension. But first of all, since we are still in 2D and 3D, well, let's see if, let me give you some examples. And, well, let's just add some vectors. We can add vectors in 2 or 3D. So V is, say, 2 minus 3, say, and W is 1 and, say, 5. So what is V plus W? Very simple. We just add them as matrices. You see, so we see that the matrix addition in fact gives me vector addition. So 2 plus 1 is 3, 5 minus 3 is 2. Okay, so that's it. So you just add corresponding coordinates or entries in this case. So the coordinates are in fact here entries. Entry number 1, this is like A11, A21 or something, and they correspond to the x and y coordinates. Well, let's find 5V. So that's 5 times this matrix. You know how to multiply a constant by a matrix. That's 10 minus 15. So you see all that we learned in the last 2 chapters, matrices, they just apply here. So we can simply say that a vector is like a column matrix. So we identify a vector with a column matrix. Everything that applies to a column matrix, in fact, applies here. Except we will see there are some other things that come into the picture, especially for in R3 we have something called cross product, which we don't see that in other spaces. It is specific to R3. So let's see. Now, example 2 is, let's say we have point P with coordinates, say, A and B is translated to point P prime with coordinates, say, A prime and B prime. Okay, so we just know how one point is translated. And let's say that we are translating every point in plane. So the question is, what is the vector that has done this translation? Okay, so what's going on? We know that a vector that translates this to this, in fact, adds to A certain number and adds to B certain number. So that A prime is in fact A plus something, say B1, and B prime is B plus, say, B2. Okay, so this gives me B1 and B2. So B1 is in fact A prime minus A, and B2 is a B prime minus B. So this vector B, the translation is simply this thing, A prime minus A and B prime minus B. Or in the matrix notation, A prime minus A, B prime minus B. Okay? So in a sense, it is in fact this thing. So let me write it here. So if P goes to P prime via some vector, some translation, then the translation is in fact OP prime minus OP. And I'm using OP prime to mean this vector, the vector that has initial here and terminal here. So OP means that. I mean this one. So OP is this. So this is OP. So OP as a vector and P as a point have the same coordinate. So OP is in fact AB. And P is also AB. Right? So that is OP prime. And sometimes students, I have seen that they prefer another notation which makes more sense to them. And they just write P prime minus P. It makes sense because P prime for us, P prime is in fact this thing, and P is this thing, that's it. So this one minus this one. But geometrically, we didn't define addition or subtraction for, say, points. But since we are not distinguishing between points and vectors, then okay, you can do that. And I guess I forgot to say what minus means because I wrote minus something. So minus V, in fact, minus say W, whatever, is in fact if minus W1 and minus W2. It's that simple. So when I said minus this thing, in fact, is plus this thing. So OP prime minus OP is in fact OP prime plus minus OP. Okay, so as vector, the subtraction means this. So when we define negative of a vector, which means the negative means what? It means the same magnitude, opposite direction. The same magnitude, opposite direction. Okay, so and you can guess that if I add W to its negative, which we call it negative of a vector, you will get zero vector. What is zero vector? That is simply 0, 0. Okay, so zero vector is simply 0, 0. Zero vector has magnitude 0, and the direction is not defined for zero vector. So a vector plus its negative will give me 0 vector. Okay. I will try from now on to use the matrix notation and not the parenthesis notation. So, example 2, let's say if P has coordinates say 2, 3 minus say 6, for example, then P prime has coordinate, and this is in R3, and say 1 minus 7, say 21, then again in R3, what is P prime? P prime, in fact, is this. That is the vector, the translation vector. Okay. So translation vector is, or can also be denoted with, this is just a notation. It means this is the initial point, terminal point. So when we are in R2 and R3, we can write, we can have notations like this, but as more than that, R4 and above, we cannot really visualize anything. We can say that. We can say this point P prime, and so on. Whatever. So this is, as we know, I said you can say it is P prime minus P, and that is in fact, you can write that 1 minus 7 and 21 minus 2, 3 minus 6. So that is 1 minus 2 is negative 1, negative 7 plus 3 is negative 4, I guess, and 21 plus 6 is 27, is it? So 1 minus 2 minus 1 and negative 4, and that's 27. Okay, so that is the translation vector, or PP prime. It's in fact this vector. Now in physics, I think they don't distinguish between these two. They just said PP prime is V above. Okay, we can say that. In fact, I wrote equal to. Okay, so I guess that's all we can just say in R2 and R3. So let me recap what I did here. So I said a vector in R2 or R3 is either like this, let's write V1, V2, or in R2, or in R3 it has 3 coordinates, or 3 entries in R3. So in fact, we can say that R2 is like this. So R2 is defined as vectors like this, or matrices like this. V1 and V2 are elements of R, real numbers, and R3 is things like that. And we define additional vectors. Let's just write it in R3. V plus W is like adding the matrices V1, V2, V3 plus W1, W2, W3, and it's simply adding matrices. So it is V1, W1, and we define scalar multiplication. KV is in fact KV1, KV2, and KV3, and we define minus V to be simply minus V1, minus V2, minus V3, and the zero vector is 0, 0, 0. Okay. So with these these 4 definitions, we have in fact given R3 or R2 certain structure, and that structure is called a vector space. So what does it mean giving some set some structure. So when we define certain operation in a set, in our case we have defined two operations. The first operation is vector addition, which is that. This is in fact definition. We just put this together and said we define vector addition to be simply adding those two matrices. And also we define scalar multiplication to be simply multiplying k by that by that matrix. So it's like multiplying a matrix by a constant. And also we define minus negative of a vector to be simply negative of that matrix. And also zero vector to be that zero matrix. So with these two operations and these two extra definitions, we make this or turn this into, give this certain structure which we call a vector space. In fact, we will see that this is true for every vector space. When we define vector space, we have to define these things. But not just that, we have to also check certain things. So we have to check these things. First of all, we have to check whether it's closed under 1 and 2. So checks. This R3 is closed under 1 and 2. What does it mean closed? It means when you apply that operation, to two vectors or two elements of this set, the result is still in the set. So if someone might say, well, I don't want to do this. Let's define vector addition. Just listen carefully. Someone might say, let's define vector addition to be this. V1, V2, V3, W1, W2, W3. Well, someone might say, no, I just want to put them like this. Or maybe just put them together like this. V1, V2, V3, and W1, W2, W3. Someone might give you these two, and they say, I don't like that. I define vector addition to be this or this, one of them. Now, what's wrong with this? Well, you just look at this and say, okay, this belongs to R6. It has 6 entries, right? This has 6 entries. Or let's say, well, we don't know what R6 is. You just say, well, R3 is matrices with 3 entries, right? These are column matrices with 3 entries. This is a column matrix with 6 entries. This is not in R3. So you added them and you ended up somewhere else. So you went out of that space. So the result of adding these two is way up there somewhere. Or this one. This is in fact the 3 by 2 matrix. So this is not in R3. R3 is 3 by 1 matrices. So this also doesn't belong here. So this vector addition, this one and this one are not good. That's what I mean by closed. When you add two vectors, you end up, or the result is still in the same set. So this is in fact here, because it is also a 3 by 1 matrix. So the vector addition is okay. How about scalar multiplication? When I multiply k by a matrix, a 3 by 1 matrix, I still get a 3 by 1 matrix. So scalar multiplication is again closed. So this R3 is closed under these two operations. Next thing is we check this thing. The way that we have defined the negative should have this effect. that v plus negative v should be 0. And it is 0. The way that we have defined it, we had this in mind to make this 0, right? Negative, 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 and just add them using that, and you will get 0. Okay? And there are some other things that we should check. First of all, this 0, 0, 0 should be in my set. That is called an identity element, in fact. So every set that you define certain operation or operations should have an identity element. And don't confuse it with 1. Identity, in fact, for some of them is 1, for some of them we denote that by 0, by 0. And most often we just denote it in mathematics by something like E, for example. Whatever. So this, when I add an element to its negative, I should get the identity vector or element, and that's it. Using this definition and using this, we have v plus minus v is in fact this guy here. In vector notation, it's like going this way. So A goes to A prime and then comes back. A double prime. So you see, identity makes sense here because it hasn't changed. A comes back to itself. So v plus minus v, v minus v, back to A. Nothing happened. So in a sense, it also means that identity means that, means nothing happened. Say, when you, it didn't move, say, in this case. So, now when we get to more sophisticated vector spaces, that's the next chapter, chapter 4, in fact, we will define vector spaces in full detail. But in fact, the main ingredient is this, and also having these two, an identity element and also a negative, what negative of an element is. So these are the two things which we have. Let me see if, yeah, and well, it's good to, but this is, so we say V equals W if they are equal as matrices. So this means that the matrices are the same, in fact, V1, V2, V3 equals W1, W2, W3, and equality in mathematics means they're the same. So this means that V1 equals W1, V2 equals W2, and V3 equals W3. All three of them should be satisfied. Okay. So that is one thing that let me see if there's anything else I should. Yeah, I have to also define Rn for you. That's also in this section. So an n-dimensional vector space or n-dimensional Euclidean space, Rn, we define it to be vectors like this. Okay, so n by 1 matrices, or n vectors or whatever we call them, that is Rn. And how do we define addition or vector addition? The same way. That is entry-wise, which means V1, V2, Vn plus W1 Wn is in fact V1 W1 up to Vn W. Okay, so that is what we call entry-wise or element-wise, whatever we call it. So that is how you add them. And two, we need scalar multiplication. And that is k times one of them. And that's like multiplying k by each entry. And we need negative of a vector. Negative of a vector should be defined. And negative v is negative v1, negative v2, negative vn. And we also need zero vector or the identity 0, 0, dot, 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 0. Okay? So this is scalar, this is this, and this is this, and this is this. Okay, so we get our ideas from R2 and R3 and expand or extend those ideas to Rn. So we identified in R2 and R3, we identified any point with a vector, and so this is the same in fact. In Rn, points are like this v1, v2, blah, 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 vn. So we identify points with vectors, and then we define addition entry-wise, and also scalar multiplication is also entry-wise, and the minus v is this, and the identity vector is the zero vector, which is what did I write? This is zero vector. Okay. So, and a zero vector, and they satisfy certain. First of all, Rn is closed under 1 and 2. Adding two of them will give me another one here. Multiplying a vector by some constant will give me a vector here, or an element of Rn. If I add v to minus v, I will get 0. And there's another one, if I add 0 to anything, it doesn't change that. If I add 0 to this, I will get this back. So 0 doesn't change neither direction nor magnitude. Adding 0. And there are some other things which yeah, I can. Well, let me see if the book really gives them. So let me just write down some properties of this and finish this lecture. We will be back to all these properties when we define general vector spaces, but let's write them here. So some properties. Property number 1 is v plus w is the same as w plus v. 2 is, I guess, 2 is this if I have u plus v plus w is like u plus v plus w. It's saying that first you can add these two, then add the result to this. It's the same as adding these two, then adding it to the first one. And number 3, I guess, is the 0. So u plus 0 is like 0 plus u, and you will get u back. 0 doesn't change anything here. And and then the u plus minus u, it will give me 0, which I told you. And number 5 is so scalar multiplication distributes, so it is ku plus k and 6. If I have, let's say, k plus m, two scalars times u, again this one distributes, and we have k, u plus k m u. But some of them are, in fact, common sense. So you wouldn't, you see, most of them, they look like properties of numbers. Properties, this is the same, and also property of number, also a number plus its negative is 0, and this one is like multiplying a number by two numbers, so it distributes, and the other way around. So, let me see if there's anything that is not that trivial. Another one is this, statistic 7, is if I multiply k by m u, it's like k m u, right? So, and 7 and 8 is if I multiply number 1 by u, I will get u back. Okay. So these are properties of those two definitions. And look, this one, it means that it commutes, it can flip. This one is it means that you can add these two first, then this one, or these two, and this one. And this is a property of the 0. 0 added to anything will give me that thing back. And anything added to its negative, a new vector added to its negative is 0, and emphasize these two. And then these are just some other properties, like scalar multiplication has this property, and this one, and that one, and the last one is if I multiply u by just number 1, I will get u back. So these are properties that you will see again in just general vector spaces, chapter 4, in fact. So this is like, over there, it looks like a review also, say. Okay, so that is what I wanted to say here. And so, see you tomorrow.